Hi gang, this is technically video number 2 for 6610. Probably noticed video number 1 ended kind of abruptly. It's one of the challenges of putting up videos at home. Sometimes you get interrupted by dogs in it, and FedEx delivery and UPS and blah blah blah. But I've got this kid working for me today in the backyard, and I'm actually building a boat dock. And I want to do the fun stuff, and I'm going to let him do the dirty work. So he interrupted me, so that's why it ended so abruptly. Really, I was done. I just wanted to give you an indication of the kind of the two areas or the two components of our program. And this obviously starts. This is the first course of what I call the research sequence. Guys, we're going to study a lot of pretty complicated designs, but I want to start out using just a one sample z-test as a prototype to get the ball rolling on some of the techniques that we're going to use. Now, we're going to develop some or I should say we're going to review some terms, alphas and betas and power and type 2, and then we're going to create some new some new concepts called effect size. Well, actually, I think in this video that's probably about as far as I'll go. This is going to be a really important video because there's going to be some things that I'm going to have you download and show you a little bit how to use something that I want you to download. So guys, let's just get it going. Statistical decision theory is probably most easily generated or motivated if we keep our first example really simple, and that's the goal here. Use a one sample z-test kind of as a beginning model. And this z-test is by far probably the industry standard, using the standard normal distribution as a model for kind of two hypothetical states of reality, if you will. Suppose we've done this. Suppose we have n equal 25 IQ scores, and we want to see which is more likely. Is it more likely that our distribution, or I said our scores, came from a distribution with mean 100, standard deviation 15? Or is it more likely that these scores came from a distribution mean 100, standard deviation 15? Now, I know back in regression 1, everybody's favorite knot was maximum likelihood estimation. I just used the word likelihood. You're probably thinking, Darbro promised us there's no theory. Guys, we're not going to do MLEs here. All right, and I know that's going to make everybody smile. But I want to look at this from another perspective. And I think it's much easier. That guy's eye looks kind of weird, doesn't it? Okay, so let's move on. And the first thing that we see here is that the distribution, this phenomena is modeled by the distribution of sample means and not individual scores. Now, what this tells us is a couple of things. The variance or spread is smaller for the distribution of sample means than for individual scores. And the second thing it tells us is, instead of standard deviation, we focus on standard error. So guys, for this situation here, our standard error is going to be found by taking sigma divided by the square root of n. In both distributions, our standard deviation, taking score, taking each measurement at a time is 15, and I kept things pretty simple here, in that the standard error would be equal to 3. So we focus on the variation of the sample means, not the variation of the individual scores. Now, we need to rephrase our question. Because our question deals with, if we take 25 IQ scores at a time, where did it most likely come from? The mean with a standard deviation of 15, or a mean of a standard deviation, mean of 100, standard deviation 15, or mean of 108, standard deviation 15. I think I'm right on that. Let me go back here and just check to make sure that, yeah. Okay, but these standard deviations give us the variation one score at a time. So we're really not asking that. We're asking which distribution did this most likely come from with standard error equal to 3. For obvious reasons, we're not looking at the distribution of scores one at a time. We're looking at distribution of sample means taken 25 at a time. Now we can create a kind of a cool chart here, and not a chart, but so let's take a look at this. All right. So the first distribution with a mean of 100 is going to be centered at 100, and it's going to have a standard deviation, standard error of 3. So I want to go 3 above and 3 below. So that distribution is going to look like this. Seeing that one standard deviation below the mean is at 97, and one standard deviation above the mean is at 103, and we know that approximately 68% of our sample means will fall from there to there. The other distribution has a mean of 108. So if I can create something down here that's centered at 108. It has a standard error of 111, and I'm sorry, standard error of 3, so it'll be 111 and 105. So if I can draw this distribution, and granted that wasn't well, but pretend it was. So one standard error below the mean is 105. Don't know why, but that particular part on my iPad won't write. And this is 111. I won't write up here either. But anyway, between here and here, 68% of our sample means occur. So guys, right here, pretend there's a, a 105, 3 units below 108, and pretend right there there's 111. It's just not letting me write on that particular part. Now, let's go on. Once we set up kind of a decision criteria, we'll start talking about an alpha level. And another dead spot on the iPad. So usually set at 0.05, and this is the probability of a type 1 error. Now guys, remember, what's a type 1 error? Type 1 error is the probability of rejecting a true null hypothesis. No. Guys, let's forget that. Alpha is the probability of rejecting a true null hypothesis. So a type 1 error is the end result of rejecting a true null. So if we set at 5%, then what we know is H sub O is rejected no more than 5% of the time when H sub O is true. Now, let's go back to our drawing, and I just want to focus on the top drawing, okay? So if I'm going in the top drawing, and let's say that we're deciding to test that is really weird that it won't let that happen down there. All right, so we're testing H sub O mu equal 100 versus the mean not equal to 100, and we're going with the industry standard, the threshold of 0.05. Well, what we're going to do is we're going to put our rejection region into two tails. So we're going to have 0.025 in this tail, and we're going to have 0.025 in this tail. Now, what we can do, because we're kind of, this problem pertains to the 108, which is above the 105, I'm sorry, above the 100, so I'm really focusing all my attention up here. But again, because the other mean that we're considering is 108. Now, if it was the other mean we were considering was like 92, then I would be concerned, with this stuff down here. But that's not the scope of the problem that I presented to you. So what I would want to do here is I'd want to find the Z critical that separates the lower part of the distribution with the top 2.5%. And you could easily do this on R. And what I would do here is I could use Q norm, and I would want area below, so that would be 0.975 from a distribution with mean 0 No, 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 no. Mean 100. Huh, I do not understand that. So our Z critical, guys, I have no idea why that won't let me write there, would be Q norm 0.975 minus 100, standard deviation equal to 3. Now let's jump over to R and do this. So I could do P norm 0.975 comma 100 comma 3. Guys, as I said, do Q norm. You guys are probably screaming at the video. So guys, it'd be 105.88 would be the line in the sand, or the sample mean, that would separate the upper tail of the reject and fail to reject region. Now I'm going through this in a lot more detail. I think one of my mistakes teaching this summer was I assumed too much, and I think actually I tried to present too much material. So you're going to see the pace slow down a little bit and maybe much more pay a lot more attention to detail, I guess. So 105.88, just let me make sure that I got that right, because we don't want to build a house on sand. All right, so 105.88, if we go back, is going to be the sample mean that separates the line in the sand. And I just usually refer to this line right here as the decision axis. So guys, if we go back to our original drawing at 105.88, which I want to draw on down. We'll call this our decision axis, and this is at 105.88. So guys, if I get a sample mean in this area, I'm going to reject the null, and if I get a sample mean on the left of that, I'm going to fail to reject the null. Now, typically, this is as far as we go in hypothesis testing model, in that we're going to either reject the null or fail to reject the null, and then it's a terminal process. You know, we're done. But I want to explore bigger, better stuff, because I know where we're headed in this class. So let's, ooh, dropped my iPad, that's cool. Let's now get into the second type of error. Called a type 2 error. Well guys, the type 2 error is denoted by beta, and the definition of a type 2 error is failing to reject a false H sub O, which you know, should be relatively clear that that is an error. Now, let's go back to our drawing here, and what we can do is we can see that this area right here would result in what? Well, if the mean is truly 108, then this is false. And if we get any sample mean to the left of this decision axis, then our decision is going to be failed to reject. So it should be clear that anything in this distribution down here this area right here would result in a decision of failing to reject from this distribution, which turns out to be the true distribution, which is the mean of 108. So guys, if we can find that area right there, then we can find the value for beta. So guys, let's go do that. So guys, beta can be found by taking P norm. What was it, 105.88 from a mean of 108 and a standard error of 3. So guys, we get 24%, don't we? Guys, you got to bear with me. My computer, for some reason, just works kind of slow sometimes. All right, gang. So we got a beta of 20. So let's summarize all this in what's often referred to as a confusion matrix. It's not going to really be a confusion matrix for you guys, but it certainly is for introductory students. So what I like to do in the confusion matrix is think about the reality. And the reality is we either need to support H sub O or H sub A. In decision making, we either, let's put it this way. Reject H sub O, or we fail to reject H sub O. Now, alpha is the probability of rejecting a true null. Beta is the probability of failing to reject a false null. Should make sense that this area is going to be 1 minus alpha, and this area is going to be 1 minus beta. Now, inserting the values for our problem, we set alpha at 0.05. We calculated beta to be was it 0.24? Telling us that the probability of committing a type 1 error is 0.05. The probability of committing a type 2 error is 0.24. Using a little bit of arithmetic, we can see that this is 0.76 and this is 0.95. Now, this upper right-hand part of our confusion matrix represents the most desirable outcome when conducting a test of hypothesis. And it actually turns out, as we have talked about in a previous class, regression, that 1 minus beta just turns out to be the power. So there is a 0.76 probability of rejecting H sub O if it's false. And guys, that is the goal of any test of hypothesis, is to find evidence to reject a false null. Now, in many, many cases, we end up with a goal of increasing power. And one way that we can increase power is to, well, let's talk about increasing power. Guys, there's kind of a give and take on the power. If our power is too low, then we might as well stay at home and not even conduct our research, because the research would be meaningless. If you don't have enough power, then you don't have any prayer of rejecting a null hypothesis if indeed it is false. If you get too much power, so if your power is really, really, really high, you get into a situation where you find differences that are statistically significant, but don't have practical significance. Now, okay. So let's. I'm trying to come up with an example on the fly here. I'll tell you what. Let's say this. Let's say at SSU that someone makes a claim that the mean ACT for entering students is equal to 21. And for some reason, we'd like to test that, and it's not 21. And we collect a random sample, and let's say that we end up finding statistical significance at the 0.05 level, where we reject the claim of 21, and we, I guess, achieve our goal, if you will. Find that there's evidence is not 21. Well, we have an extremely large sample size here, and we find out we have tremendous power, and we construct a 95% confidence interval. And we get a confidence interval that looks like this. Now, granted, that entire interval is above 21, but it's representing the fact here that the true mean, which again is bigger than 21, 21.01 is bigger than 21, 21.03 is bigger than 21, we have statistical significance, but I kind of want to appeal to your common sense here. Do we have practical significance? As an admissions director or placement coordinator, would we really care of a difference of 21 and say 21.02, 21.03? It would make no difference whatsoever. So here's a situation where we have, I came up with just on the fly, that we have a situation where we have statistical significance, but we wouldn't have a practical difference, practical significance. Well, guys, enter in what's called effect size. And effect size at the end of the day gives us a standardized measure that can tap into the effect of the study. And the beauty of effect size is, again, it's standardized, so it gives you a method by which you can compare results from different studies. If you look at just p-values, which are clearly a function of sample size, those things aren't comparable across different research designs. Now, guys, there's going to be about 4 or 5 different types of effect sizes we're going to use. The one that I only want to give you 2 right now. The first one is what we call Cohen's R. And Cohen's R kind of works on the following scale. This would be a small effect. This is a medium effect. And this would represent a large effect. Probably the most widely reported effect size is called Cohen's D. There's only one place in this class we're going to use Cohen's R because the calculations are just simpler. We're going to use Cohen's D, and then we're going to get into something called eta and eta squared, which are completely different. But let's keep it simple. Let's crawl before we start running sprints. Cohen's D works on the following. So 0.20 gives us a small effect. 0.50 gives us a medium or moderate effect, and 0.8 gives us a large or high effect. So these are the benchmarks to make these calculations. Now, trying to sort through everything I want to get through. I tell you what. Let's put this to work. Now, let's not put it to work just yet, guys. What I need you to do is the following. All right. So let's get out of this, and I want you to go to Google or whatever search engine that you prefer, and I want you to type in GPower. And I'll tell you what, guys, hold on just a second. I need to check on something. Okay, I'm back. If you go to GPower, what I want you to do is go down to the UCLA. It's GPower data analysis example. And what GPower does, it's probably the most commonly used program for calculating power, effect size, and so on and so forth. And you can go down there and look at some stuff if that's what you want to do. But at this stage of the game, what I want you to do, there's a link right here that I want you to click. And I want you to go through the download process. So let's see where you download this. Yeah, you get down here. So you get down to downloading GPower for either Windows or for Mac. And guys, I've already done this, and I need you to do this too. And when you get done, you're going to see GPower on your desktop, if that's where you choose to save it. So I'm going to open it up and show you kind of what it looks like here. The first thing you do is you get over here to the test, the family of test, and you got z-test and so on and so forth. So if I go to z-test, there's different different things that I can use there, logistic regression, so on and so forth. We're going to use chi-square test and f-test. We're going to use f-test quite a bit in here. So. But what you can do, for example, if you're going to run just a simple t-test, you can come down to well, I mean, yeah, I have all sorts of different options there. Two sample t-test and t-tests for different slopes and different things. But let's keep it simple today. So if I run this, what I can do, this part over here, this left column is the information that you put in, and then you'll calculate, and it'll give you what you need. So let's say, for example, well, the two things I want you to focus on is creating a what sample size would create a particular power. So that would be a well, you get it, which would allow us to compute the sample size given a certain effect size and a desired power. There's also a post hoc down here that can compute the achieved power given certain things. So I'm going to minimize this right now and go back to what? Let's go back to the blackboard. And for some reason it's kicked me out. That's interesting. There's no option for AirPlay. There it is. Ah, the nuances of teaching online. But there's nuances in classrooms as well, okay? So guys, let's carry this out. And I want to carry it out and show you GPower and some new stuff. All right, so you read in a newspaper or something. Reports that the SAT for all high school graduates has a mean of 500, standard deviation of 110. Now, I'll tell you what. Let's not do that. There's a reason I don't want to do that. All right, because I want to show something new. Okay. So this says that the mean SAT for all high school grads is 500. Now you kind of suspect this. For students, actually high school grads, in your school district, because you think, isn't it comforting that your professor can't spell think? Because you think the mean for your kids, well, not your kids, is higher. So what do? You collect what's called a simple random sample. And let's just say that you had access to a random sample of 100 high school graduates in your school district. And so we're going to carry out the test. Of 0.05. All right. Now, as usual in this class, we're going to use technology. I promised you that the theory was going to be really relaxed. So what I would want to do is pretend that we've collected the data. Okay, for some reason that doesn't want to go away. Huh. Okay. Well, let's just get rid of you then. So we've collected some data here, and I've already got it up. Notice that I've already saved it on my desktop of, I have no idea what that means. And what's happened is someone has gone out and either randomly selected some SATs or whatever it may be, but you can see that they have collected 100 SATs from the school district. All right. Now notice that guys, sorry for the delay, but I've got to wait on the computer to do its thing. Notice that the file I've saved it on my desktop is act.sav. So what I want to do is, as we usually will do in this class, we'll use R to do the calculations for us. So, guys, first thing I got to do is set my working directory. And then I want to get my data. And of course, then I have to attach my data. And I like to, at this point, get names. That just tells me the variables that I have. So I have the ID and I have the SAT. Okay? And let's just take a look at these 100 kids. They have a mean of 536.82. Which clearly kind of substantiates or at least validates the motivation of this person to test that the claim is 500 or above 500, because it clears it. It may very well be so. Again, remember, we're using a sample here. This is just for 100 students, so we can't compare straight up 536 and 500. We have to let the process play its way out. So our standard deviation is 117.46. Remember, this is the standard deviation for the sample of these 100 students. Well, the next thing I would want to do is carry out a t-test. And I would want to carry out this on SAT, where the mean is 500. And we have a unique case here. Well, not unique, but it'd be kind of unique in this class because we'll typically test not equal to. We typically conduct two-tail tests, but this way, this is a situation where it seems appropriate to conduct a one-tail test. So alternative greater. Guys, if we had wanted to do an alternative hypothesis one-tail less than, we would just type less there. If you leave this out, it will conduct a two-tail test, which I'll do in just a second for a certain reason. Now, if I carry this out, you can see that my test statistic is 3.13. I have 99 degrees of freedom, and I have a p-value which is less than 0.05. Now, this is one thing I don't like about R. It calculates the confidence interval based on a one-tail test, giving you infinity either at the right bound or the left bound, depending on whether you conducted a greater than test. For example, if we test a one-tail greater than test, my right bound of the confidence interval will be infinity. If we tested less than right here, then the left part would be negative infinity. I don't like that. I want a 95% confidence interval with numbers. So what I would do then, even though the goal here is to conduct a one-tail test, I would run a two-tail test, and I can see that I get a 95% confidence interval that has two real numbers. Now, notice your p-value has changed, but don't lose sight that in running the one-tail test, this is the p-value that we need to make our decision on. But this is the 95% confidence interval that we would use. All right, so the next thing we would want to do is we want to see, we see that we clearly have statistical significance. So we would next want to come in and calculate the effect size. Amazes me how slow this thing is. Alright, so I've lost connection with this, so let's bring it back. Yeah, let's maximize it. Okay, so in this situation, Cohen's d effect size is very easy to calculate. It's just the difference in standard deviations, not standard errors. So again, notice the effect size is trying to take the sample size out of it, because as we increase sample size, if we increase our sample size enough, we're going to reject everything. So it wants to take the sample size out and just get a standardized measure of the difference between the sample mean and the population mean. Now typically where Cohen's d really comes in to be handy is when we look at treatments and we're looking at the population difference of population means. But we're looking at this in the simplest case. So what we're going to do here, we will have 5, well, I don't remember. So let's go back and take a look at it. I think it's 533.87, but I did this in a previous video once. Assumed I remembered, and it worked out. No, so 536.82, so I'm glad I didn't. So guys, the effect is going to be the absolute value, so all I have to do is just think that I'm going to use the positive. So 536.82 minus 500 divided by the standard deviation, which is 117.46. I never would have remembered that. So the effect size is 0.31. Now, if we go back to the standard on Cohen's d, we'll see that 0.31 falls somewhere between the small and the moderate range. The small is 0.20, the moderate is 0.50, so it's actually closer to the, so I'm going to pull up political tactic here and place center. Our effect size is small to moderate. So our effect size is 0.31. Now, what I want to do now is I want to get out of this and go to this GPower that I've asked you to download. And let's see what we can get into here. So